Nothing lasts forever, but how long does a component last? How long should it last? Can we design for a chosen life? For metals, can we foretell fatigue-free life? Nature equips us with components made for our lifespan. Evolution has developed and optimized this design over millions of years. Engineers must design and build components much more quickly. At first, engines would break almost as soon as they were started. The design was changed. Components were made stronger, bigger and heavier in the process. Low-stressed machines like this one could then run for 100 years without failure. But sometimes they would work perfectly for hours, days, even years. And then, for no apparent reason, a metal component would break right across. No sudden increase in load or stress. The metal had failed by fatigue. A tiny microscopic crack-like flaw, usually on the surface, would start to grow, slowly at first, as the metal was continually flexed. The crack progressively lengthens, accelerates, until finally breaking apart. Here you can see evidence of fatigue. These are the so-called beach markings, often where the crack was arrested for a period and subsequent corrosion has left a permanent record in the wake of the crack front. And on an even smaller scale, at a magnification of 1,500 times, you can sometimes see striations, ridges on the fracture surface due to plastic deformation at the crack tip. Each striation indicates one quantum of crack growth. Many components have to be safety critical. For example, steering components of a motor vehicle. And miners trust their lives to the brakes of the colliery lift winding equipment. Even if life isn't at stake, money often is. Expensive machines must work hard and long with the minimum of stops due to breakdown and repairs. Consider all the components of a car engine. Obviously, not all are safety critical. It will still work with a broken valve, connecting rod, even piston, but not at all well. Imagine the fuel savings if every moving component could be made lighter, cheaper, and more reliable. Since most breakages result from metal fatigue, it would greatly aid in the development of more efficient components for a designer to know in advance what the actual service life of a particular component will be. Only then can he critically evaluate each new idea rapidly and ensure a shorter time between design and production. In recent years, a system has been developed to predict when fatigue failure will occur, and hence to foretell the useful or effectively fatigue-free life of a component. Dr. Peter Watson.
This system of life prediction has been made possible by two things: recent advances in our knowledge of metal fatigue and fracture, and much more significant, the dramatic improvement in our equipment during the past decade. For example, we can now measure material properties much more accurately than before. We can quantify a material's resistance to crack initiation and crack growth relatively simply. In the area of stress analysis, we can analyze the stress distribution in complex shapes using finite element analysis. And in the area of service loads, we can measure loads much more efficiently than ever before. And once we've measured them, using a computer, we can carry out sensible and useful analysis. In this area, as in all the others, the computer is critical to this improvement.
Before seeing the computer in action, we'll examine the inputs in turn, starting with the cause of stress in the material, the actual loading on a particular component. Here's a typical situation. All the components of this car suspension system experience a complex loading spectrum, certainly not steady or even cyclic. So we must measure actual loads in service on either existing or prototype replacement components. But how? We make the test component into a load cell by attaching strain gauges at convenient points. These will not necessarily be the points where strains are greatest. Such places as screw threads or sharp corners may be inaccessible or unsuitable for gauges. Loads can be inferred by comparing the strain reading with a previous calibration of the strain gauges using known static loads. Here, the drive shaft of a front-wheel drive car is being instrumented. Since the component rotates, the signals from the strain gauges are applied to a small radio transmitter fixed near the gauges on the shaft itself.
We check the jams.
Gauges are also attached to monitor the vertical displacement as the wheel bounces up and down, and additional transducers are used to measure speed and steer angle.
That's fine.
When the car is driven hard on this test track, the signals from the gauges are recorded on tape, either on board the car itself or by a special data receiving and analysis vehicle parked close to the track. Inside, the signals are continuously displayed and monitored on a multi-channel chart recorder.
Approaching the Crown Bend, 35 miles an hour on the Crown Bend, third gear, 3,500 RPM. Speed 40 miles an hour. Left hand, 6-degree adverse camber bend.
The driver's voice is also recorded to help identify the signals later when the data are reproduced.
Entering the pitching straight into fourth gear, 45 miles an hour.
Typically, in a front-wheel drive car like this, 4 signals would be speed, torque, jounce and steer. Jounce is jargon for bump and bounce. It matters little whether the strain variations are fast or slow. Fatigue damage depends only on the amplitude and mean level of the strain cycles, and not on their timescale. So the computer must first convert these continuous variations of strain into a set of numbers. It must count strain cycles of given amplitude and mean value. One way to do this is by rainflow counting. For example, suppose we take this simplified strain history and rotate it through 90 degrees so that time is now flowing downwards. Imagine rain falling on all the sloping surfaces. The principle of rainflow counting is to join up the flow from inside and outside slopes to form complete cycles. Vertical drops are ignored, and double flows along the same slope are counted only once by the higher source flow taking priority.